everyone, welcome to another lecture for drug delivery engineering and principles. We have been discussing quite a lot of mathematics and quite a lot of how to compute different things for determining release rate, for determining how the drugs are being distributed in the body. So, I thought this in today's class we will just give you a little bit of exercise and we can walk through some of the questions and solutions to those. So, that will help you in terms of first of all relating as to how these are being used in actual clinics and how these problems can be solved, and then it will again help you in your exams and assignments because some of these problems will be similar to what you may expect in your exam. Okay. So, to start off let us do sort of recap of whatever we can do. I have planned out about 6 or 7 exercises in this lecture. So, let us get into that. So, here is a question, the question is for a drug X. So, could be any drugs, could be any of the drugs, maybe any drug that may cause hypertension, that may relieve hypertension, that may relieve diabetes, could be anything. For a drug X to be therapeutically active, its initial concentration in the plasma should be above 10 microgram per ml. So, and that is in an adult human. So, basically what we are saying, if we have a drug X and for it to be therapeutically active, we need to get this concentration to be 10 microgram per ml or greater. Now, this is again very clear. I will also explain a little bit as we go along. So, we know that for every drug there is this toxic level. So, this is if I say concentration of the drug. And then there is some subtherapeutic level. So, this is toxic, this is subtherapeutic, and let us say this is time. So, for any drug we can define these two parameters. Obviously, if you keep giving the drug and it reaches a certain amount, it may start becoming toxic to the body, and below a certain amount it will not even do anything. So, it will be as if there is no drug, and this is the region you want to work with. Basically the working range. Now, for this particular drug X, we are saying that this value is 10 μg per ml. Obviously, the upper limit is not given in the question. So, we will assume that somehow we need to get the concentration above this particular value. So, now this drug is also known to distribute in the total body water. So, now that comes to a discussion on the VD, which is the volume of distribution, and it is saying that this drug distributes throughout the body water. So, what kind of drug this will be? This will be fairly hydrophilic drug. And so, the question is how much drug should be injected so that its concentration reaches the therapeutic levels. And then the question is asked us to assume that the drug is rapidly distributed and make and state other necessary assumptions. So, obviously, if we talk about real clinical scenario, we need a lot more information which is not given in this question, because technically we should know what is sort of the elimination rate, right, because let us say I inject a drug, but even before it goes to the 10 μg per ml it starts eliminating also. So, I need that rate also. So, that is why one of the assumption that they are saying is that it is a rapid drug distribution. So, we can assume instantaneous for this problem, and then of course, there are a lot of other assumptions we have to make as to what is the weight of the human, what is the total body water present. So, all of that assumption we will make as we continue in this. So, from our discussion in the class, let us say for an adult human the total body water is about 30 to 50 liters. That is what we discussed, right. So, let us take an example of 30 liter, and then we know what VD with the volume of distribution is amount of the drug in the body. So, basically how much you are injecting divided by the concentration in the plasma. Right. So, we know that if Vd is very high, that means that the concentration in the plasma is fairly low, which basically would suggest that it is a lipophilic drug. But in this case it has been given that the Vd is actually the total body water. So, let us assume this to be 30 liter. Right. Now, since we are saying that we want the therapeutic concentration to be 10 μg per ml, the concentration in the plasma, which is again a part of the body water, should also be 10 μg per ml. So, what we can then do is we can then just say that 30 liter is equal to the amount of the drug in the body, which is the total amount that we are injecting given its instantaneous distribution, and we are neglecting any elimination. So, let me state this. So, here we are neglecting elimination, at least for the time frame that we are talking about here. So, now we go with this, we are saying that 30 liter should be equal to the amount of drug in body divided by the concentration in the plasma, which in this case is 10 μg per ml. So, then the amount of drug in the body, that is basically what we are injecting, is equal to, so let us say that is A, is nothing but 30 liters multiplied by 10 μg per ml. So, let us just convert μg to this ml to liter and μg subsequently. So, if I say so 10 μg per ml would be nothing but 10 mg per liter. All I have done is multiplied both sides by 1000, and then 1000 μg is 1 mg, and similarly 1000 ml is 1 liter. So, then we can say that this is 30 liters multiplied by 10 mg per liter, liter we can cancel. So, that will become 300 milligram. So, that will be the amount of drug that we will have to inject, and that will lead to the concentration of 10 μg per ml. Obviously, in a real scenario we will have to inject a lot more than this, because there will be elimination as well, and then we again want to be above this, not at this, and so that is why it will be this. So, 300 milligram is the bare minimum that we will have to inject for the drug to be actually therapeutically active. Obviously, if we would have assumed the total body water to be 50 liter, this would have just turned into 50 liter multiplied by 10 mg per ml or 10 mg per liter, giving us a value of 500 milligram. So, now you can see how the doctors can then if a patient comes in and the patient is tall and heavy, then they will have to give a lot more drug, versus let us say if it is still a kid or some person of that size, and that is why the doses also differ between women and the men, because typically there is a difference in the weight also. Okay. Okay, here is another question. So, in this question again, this is more on the first part of the talk, first part of the course, where we are talking about pharmacokinetics. So, in this particular question what has been given is a drug X has an infusion rate of about 100 microgram per minute. So, basically we are saying that drug X is infused at 100 μg per minute. So, maybe it is an IV drip. You have seen if you go to the hospitals they will have this stand with a bottle and connected to your veins through a tube. So, maybe it is something like that scenario, and where they are allowing about 100 mg of drug to go in per minute. And how would they do that? Maybe the drip has a concentration, then they are releasing maybe 0.1 ml per minute, and that comes out to be 100 micrograms. So, something very achievable. and then now they are talking about elimination here as well, and they are saying the half life for the elimination is about 15 hours. So, we know that T half is equal to 15 hour. Then they have given the rate of elimination also. So, the Ke, which is the rate of elimination, is equal to 0.1 per hour. Okay. So, and then the Vd is also given to be 40 liters. So, again this Vd is fairly high, which means that the drug must be hydrophilic, and given our previous problem it also appears that it is also distributing in the total body volume. And so, now they are asking what is the steady state concentration. So, let us say I write the steady state concentration as concentration at steady state. So, this is what we want to find. Now, let us look at the scenario. So, we have a patient, the patient is being continuously given the drug by a drip, but we are saying that the drug is not going to be stable there forever, and it also has some elimination rate, it also has some half life. So, then how much should I give? So, again if I draw that curve again, so again this is the toxic level, this is the subtherapeutic level, we have concentration versus let us say time. Now, in the previous example what we looked at, how we can get to this particular range. Now, what now we are trying to do is to see if we can maintain in this range. So, let us say if we are here and we want to maintain it in such a way that it does not really go away from this particular range, then how we have to continuously infuse it, because this drug is degrading, and if we now continuously give the drug, then it will remain in this range. So, in this particular problem, since we are saying the drug is also getting eliminated, we have to balance for that. However, the metabolism of the drug is not given. So, in this case we will assume that there is no metabolism, or even if there is metabolism, it does not really change the activity of the drug. So, maybe the metabolites are also active, or maybe there is no metabolism, which is again not a physiological case. There will be some metabolism as well, but for now let us assume that there is no metabolism, it is only infusion and elimination. So, now if that is the case, then at steady state, since the drug cannot be generated in the body, what we will say is let me do a mass balance here. So, drug injected plus drug generated, this is inside the body again, minus the drug eliminated should be equal to the drug added at that particular time. Now, we are saying a steady state, so drug added is 0 at that particular, when I say drug added is in like the increase in the drug concentration, but it since it is steady state. So, let me just actually say is equal to the drug concentration increase. So, this is 0 because it is steady state, we are saying that the drug cannot be generated. So, this is 0. So, then what we have is basically drug injected is equal to the drug eliminated. This is nothing but a mass balance. Right. Now, let us look at each of these. So, we know that the drug injected is already is 100 μg per minute, and what about the drug that is eliminated? So, let us assume that well, we do not really need to assume because the Ke is given to us. So, what is Ke? Ke is the rate of elimination, and its units actually it should actually also so if I then equate it to the Ke multiplied by the concentration of the drug at that time. So let us say the CSS, because we are saying that is a steady state concentration, so that is not changing. So this should then equal, because this is the amount of drug that is getting eliminated per unit time, and this is the amount of drug that is getting injected per unit time. So if now that is the case, then it becomes simple. So all I have to do is say that the Ke we know is 0.1 hour per hour multiplied by the CSS, and that should give me the steady state concentration. So then CSS will basically become 100 mu g per minute multiplied by, correct. Now I have to match these units. So to do that, what I can do is I can convert this. So I can multiply by 60, I can convert this to hours so that I can cancel this. So this will basically become 60 multiplied by 100. So that is now mu g divided by hour. This then gets multiplied by hour divided by 0.1. So the hour can get cancelled. So this essentially will become 6000 and then one more 0 mu g, which you can convert to milligram. So that will give you about 60 milligram. So now this is the total drug that is going to be present in the body at steady state. Now we know that the Vd is 40 liters. So that means that this amount of drug will be distributed in this volume. So then the concentration will be nothing but 60 by 40 milligram by liter. So that will basically give us 1.5 mg per liter, or you can convert it to whatever unit may be desired. Okay. So let us look at another question now. So now we are moving towards the diffusion part of the course, and the question is in this case is how much time it will take for a protein with a diffusion coefficient of 5 into 10 to the power minus 7 centimeter square per second to move the root mean square distance of 1.5 meter. So now what is 1.5 meter? That is, you can consider is, let us say, a length of a person, right. We are anywhere between 1.5 to 2.1 meters depending on how tall or short we are. So basically the question is asking how long will it take if I have a protein, let us say, in my brain for it to reach my feet, if it is just by diffusion. So this is a very simple question in this case, because we know that the root mean square x RMS is nothing but root 2 dt, right. And so now what we know the x RMS, we know the diffusion coefficient for that particular drug in that media or that particular protein in that media, and then we want to find out how much time it will take. So let us do this. So this will basically become, if I square both sides, it will become x square RMS is equal to 2 dt, which will then further become t is equal to x square RMS divided by 2d. So I just want to point out that this diffusion coefficient which is written here is actually fairly physiological. This is how the typical protein diffusion coefficient is what you will find in the literature, and again the distance that is given here 1.5 meter is again very physiological as well, because that is what, at least for human case scenario, you will find this being the sort of the requirement for the proteins to go throughout the body. So now if I solve this, so we will get T is equal to, so in this case x square, which is 1.5 divided by 2, and this is obviously meter and meter, divided by 2 multiplied by 5 10 to the power minus 7 centimeter square by second. So this will then become 1.5 multiplied by 1.5 meter square second divided by 10 to the power minus 6. So 2 10 and 1 subtracted centimeter square. Now I can't cut this out, tell they are in the same unit. So I can then change this to 1.5 multiplied by 1.5 meter square divided by, so 1 centimeter is 10 to the power minus 2 meter. So that will become 10 to the power minus 6 multiplied by 10 to the power minus 4 meter square, and of course second here. So now the meter square can get cancelled. So this will then give us T is equal to, so 1.5 multiplied by 1.5 multiplied by 10 to the power 10 seconds. So now this is quite a lot of time, right? I mean, if I convert this to, let us say, hours, I will basically do, so this will be hours. If I now actually want to convert this into years, it is going to become this, this many years it will take for this protein to diffuse. Now even with all this, if I see here now, so I am talking about 1 2 3 4 5 6 6, so I am still talking about hundreds or thousands of years. So almost about 500 years or something. So I am not going to go ahead and solve this right now, but we are talking about this is going to be greater than hundreds of years. So now you can imagine, like, if we want to if we are saying that a protein, if it is moving purely by diffusion from our head to all the way down to our feet, is going to take about more than 100 years, then we have a big problem, right? Because eventually all these proteins, all these biomolecules need to move freely around. So what are the different things that we can change about that? Obviously that is not true, right? Because we know that that is not true. We have insulin secreted one part of the organ, but immediately goes to everywhere else. We eat food, even though it gets absorbed through our gut, it goes to all the parts of the body. So that is where the circulatory system comes in. Because if we do not have the circulatory system and if we require only diffusion, then we are taking years for that. In fact, this is much more than the lifespan of the human. So that is not physiologically feasible. So maybe that is where the evolution of the circulatory system started, to solve this diffusion problem, this transport problem that we had. So the only way otherwise is you change the diffusion coefficient, which of course you cannot. Some molecules do have higher diffusion, but even if you have a 10 times higher diffusion, even then we are talking about years. So the circulatory system is obviously very fast. Our heart beats pretty much 100 times a minute, and that ensures that everything is well distributed to all the parts, even though between the two blood vessels there might be gaps. So let us say here there are two blood vessels, and this region will still require diffusion of the protein from here to here. First of all, some kind of transport receptor to take this protein and shuttle it across if it is not freely diffusing through the blood membrane, and then once it comes out here, it still needs to diffuse in to reach the site of action. And but then this distance is then reduced to about 50 microns, 50 to or 100 microns, let us say. So we are talking about hundreds of microns here, and now if I substitute that, that changes a whole lot, because 1 micron is nothing, or let us say we go with this. So 100 micron is nothing but 0.1 millimeter, which is nothing but 0.1 multiplied by 10 to the power minus 3 meters, or basically I can say 1 into 10 to the power minus 4 meters. So, now if I square this which is being done here, you will find that this is going to become 10 to the power minus 8 on the numerator, and that will basically meaning so if I now substitute here for this, then we are talking about t is equal to 1 multiplied by 1 multiplied by 10 to the power minus 8. So, this is for 1 instead of 1.5 meter here, and then all the numerator will convert to 10 to the power 10 seconds, which is going to give us about 100 seconds. So, because of this circularity system, we are able to reduce the time of diffusion from hundreds of years to hundreds of seconds, which is much more relevant in our case. That is why the circularity system helps us in quite a lot to carry our normal processes. Okay. So, let us look at the fourth example now. So, let us see what this example is. This is more on the reservoir system now. So, we are moving further as towards the middle of the course, and let us see what they are saying. So, they are saying we have developed a spherical reservoir with a diameter of about 10 centimeter for a sustained release of the drug X. So, obviously this is a reservoir, maybe there is some thickness to this membrane which is also given to be about 10 micron, and all of this is filled with let me use another color. So, all of this is filled with the drug X, and this is of course a polymeric membrane, and this reservoir system allows this drug X to diffuse in through this membrane to come out, and this was designed, a certain amount of drug was loaded into this. However, at any time t we found that only 0.5 milligram of drug is coming out. Okay. So, but for our application we want the drug to be about 10 milligram at that particular time t. So, we are almost 20 times lower than what we are supposed to do. So, the question is then what should be the polymer membrane thickness be to achieve this release rate. So, this is the first part of the question, and then there is another part that will tackle sequentially. So, so we know that for a reservoir system the amount of drug released MT is nothing but the area, the diffusion coefficient, the partition coefficient of the drug, the concentration of the drug in the membrane multiplied by time t, and the total thickness of the membrane. So, this we know for a reservoir system. So, now in this case we know if we substitute this, we are saying that 0.5 milligram. So, we do not know a lot of these values, but that is okay, we will let them be at time t, and we know this thickness to be 10 micron, and now we are saying what should be this thickness, so that this value becomes 10 milligram instead of 0.5 milligram. So, again these values for the same device will remain the same including the time, since we are saying at the same time, but what will change is this value, which will let us say we say is L, the new thickness. So, what we can do simply is just divide these two equations. So, 0.5 by 10 milligram is equal to ADK CST by 10 micron on this side, and then for the 10 the other equation is ADK CST by L. So, obviously these two get cancelled, and what we will have is 0.5 by 10 will be equal to L by 10 micron. So, this can L can go on the other side. So, we will have this thickness to be 0.5 micron, which means that if we now decrease the thickness from 10 micron to 0.5 micron, we will be able to achieve that. So, this is nothing but a 500 nanometer polymer thickness layer. Okay. So, let us see what the next part of this question is. For this new membrane thickness, can you now change the diameter to achieve original release rate? So, now it is saying that okay, we do not want to change the thickness anymore, the thickness will fix at 500 nanometer, this new thickness, but what should be then the diameter of the device to be able to change this. So, then it is fairly straightforward again. So, we will apply the same equation. So, let us remove this. So, now the values that are given to us is this, that 10 milligram, which is the released amount, is, let us say now, because we are changing the diameter, the area will change. So, I will define them as A1 and A2 will be dkCST by L. L in this case will be 500 nanometer. So, I do not need to change that, but what we want is in another case we want the original release rate. So, another equation in the new device will be 0.5 milligram will be equal to A2, the new diameter, dkCST by L. So, again we can do the same thing, we can divide them again. So, let us say 10 by 0.5 will basically become A1 by A2, where A1 is the current diameter, A2 is the, or A1 is the current area, A2 is the new. So, we can then expand them as well. So, we know that area for a spherical will be 4 pi r square. So, or pi d square, this is a sphere, remember. So, pi d1 square by pi d2 square. So, pi can cancel, this is going to become 20. So, 20 should be equal to d1 square by d2 square. So, now what you can do is you can then solve for this and get the ratio of these two. So, if I want a ratio, I can just do a square root on both sides. So, square root here, and then if I do a square root, this is going to get removed, and now I can find that how I can change the diameter. I can increase it by certain amount, I can decrease it by certain amount to get the original release rate. Okay. So, here is another question now. This is on the polymer matrix system. So, the question is, a current treatment for the disease involves giving a drug, in this case the drug is mentioned as rapamycin, for 1 gram tablet, which is given twice a day through oral route, and this particular treatment requires it to be given for about a year. So, quite a lot of drug that the patient has to take. The absorption of the drug through the oral route is about 10%. So, for this particular drug rapamycin, we are saying that it absorbs for through the oral route at about 10%, and now you have been asked to design an erodible polymer matrix. So, your task is to design an erodible polymer matrix, so that the patient does not have to continue to take these tablets twice a day for 1 year, which is very patient non-compliant. It might be easier to just do one sort of implantation, and that may able to release the drug for the whole year. So, that is what you want. So, you want a polymer matrix which is erodible, and once you implant it with once, it should last for the whole year with the same amount of drug being delivered. So, this is the question that you have in hand. You know that whatever polymer you may use for this particular drug, you may be able to achieve a maximum loading level of about 5% in your implant. So, remember what the loading level is, it is the amount of the loading level is basically amount of drug, or I should say amount drug by the total amount of the implant. So, this I am saying is 5%. So, explain whether it is a, so even before you go into designing such a system, you want to see if this is even feasible. So, we want to see if it is rationally feasible to design such a system, and you can assume whatever polymer you are using, its density is 1 gram per ml. Okay. So, now given all that, you are seeing if it is feasible. So, let us see what we can do. So, we know that the amount of drug that is being given. So, amount of drug per tablet is 1 gram. So, and then this tablet is taken twice a day. So, amount of drug per day is 1 into 2, which is 2 grams that is being taken. Now, this is being taken for 1 year. So, amount of drug per year, and obviously we are only talking about 1 year, is 2 gram and then 365 days. So, this is the amount of drugs that is being given. So, this will basically become 730. So, we need to give 730 gram of drug for full 1 year. Now, but obviously this is the amount that we are giving, but the amount that is getting absorbed is only 10% of that, because we are saying that oral route we only get 10% into the system. So, amount of drug which is bioavailable for the whole duration is about 730 multiplied by, since it is 10%, so 0.1, which will give us 73 gram. So, now we are saying that if we are implanting something, and since we are going to implant this in the body, everything once the polymer degrades will come and remain in the body. So, we want to somehow make a device which has 73 gram of the drug. Okay. So, now having done that, we know that the loading level, so maximum loading level we can achieve is 5%, which means that if I want 5% of the drug, then I need to have a rest as polymer. So, then what is the total amount of implant that we need to put in? So, that will be nothing but 73 gram is what we want to put in, multiplied by 0.05. So, that will be the total implant device, and this will if you solve this will give about 1460 gram of the total implant weight. Now, we are saying we can assume the polymer density to be about 1 gram per ml. So, this will basically mean 1460 liter or 1460 ml total implant volume. Now, this is huge. I mean, this we are talking about again 1.46 liters, which is huge. It is really, through any route you would not get that much space to put in your implant. So, this is fairly looking improbable to be able to design, and this is assuming quite a lot of things, that there is a 5% loading level, which is actually fairly high. So, in general we would have to conclude that this is fairly rationally not possible. However, if you can somehow increase the loading level and get it to, let us say 80%, 90%, then we are saying that it is fairly feasible, because 73 gram or let us say 73 ml is not such a big volume. It is something that can be implanted, but in this particular case the value comes out to 1.46 liter, which is not feasible. Okay. So, here is the last example. So, in this case we have been given that a non-degradable polymer matrix slab was prepared with about 100 milligram of drug dissolved in it. So, and we are saying that it would release about 5 milligram of drug after 24 hours. So, the question is then how long will it take for the drug to be released, the total amount of 25 milligram. So, that is the first part of the question. So, let us tackle that. So, we already know that for a polymer matrix lab the equations are these for the early and the late time through our class. So, and this is of course after approximation for early time and the late time, where early time is anywhere between 0 to 60% of the drug being released, and late time could be anywhere between 40 to 100% of the drug being released. So, in this case we are saying the total drug that is loaded is about 100 milligram, and what has released is only 5 milligram. So, if I do this calculation, so this will be nothing but 5 into 100, and that is only going to be 0.05 milligram, and even for how long will it take for 25 milligram, we are still talking about 25 milligram by 100, that is still only 0.25, that is still only 0.25. So, in both of these cases we can use the early time example. So, we will use the early time example. So, let us see. So, if we are saying that 0.5 by 100 is equal to, from the first equation, sorry not 0.5 but 5 by 100, which is the 5 is released and the 100 is total, is applying this equation is 4 dt by pi L square root. Now, if this much is being released for this given length L. So, if you look at this equation, the only thing that you can change for the device geometry is L, but we will come to that later. So, if this is the case, then how much would it take? So, this is a time t, let us say this time is 24 hours in this case. So, to get to 25 milligram, so if I do 25 by 100, so this time will have to then increase by, this whole thing will have to increase by 5 times, because this is 5 times of this. So, then the t, since it is in square root, will have to increase 25 times. So, this will basically mean that the new t t new would be 25 times the original t, because that is 25 is going to get square root to 5 and then it is going to become 25 here. So, since we are saying it is 24 hours for 5 milligrams, so it will take about 25 days for 25 milligram. Now, we want to increase this release rate, and we are saying in the second part, we are saying how would you change the device geometry to result in a release of 2.5 milligram of the drug after 24 hours. So, we want to go back to 24 hours, but we are saying that we want 2.5 milligram now. So, actually decrease the amount of the drug that is being released, we wanted to release it much longer time. So, we can still use the early time, because we are still talking about much lower amount of drug than the total, and so if we do that, then the only parameter we can change here is L, which is related to the device geometry, everything else has nothing to do with the device geometry itself. And if you look closely, this is L square, which is square root, so this is nothing but it is a function of 1 by L. So, if I now want to decrease the release that is happening to 2.5 milligram from the original 5 milligram, I would have to then change the L subsequently, so that it becomes the whole thing becomes less by 2 times. So, the L would have to change accordingly. So, this is fairly easy to find out. Okay. So, this is what I wanted to tell you in terms of exercise, just some basic knowledge about how to solve this, how to go about, how to apply this in actual practice, and I hope most of this is understood. So, thank you.